Welcome back, friends. Let's have another lecture on fluid mechanics and rate transfer processes. We are going to continue our discussion on control volume analysis and look at how the analysis can help us model a fluid motion. So today we are going to talk about the momentum theorem. Or we can also refer to it as force balance. So we are again going to begin with the Reynolds transport theorem. So let me recollect for you the Reynolds transport theorem, which said that if I have a certain property, so eta is my specific property, and n is the total property in CV, and we had talked about the CV as something like there is an exit port, there could be an entry port, and we have a CV something like this, and there's fluid coming in and fluid going out. So we said that if I want to look at del n by del t, which actually is, so n here is the volume integral of eta rho dV. This is given by the material rate of change and minus the efflux, which is over the control surface rho v dot dA, and of course the eta sitting here. So the idea was that the accumulation inside a control volume of the property is related to the growth of that property, the material rate of that growth rate of that property inside the control volume, and then there could be a transport of fresh eta coming in and some eta leaving out. So the net of that, that's the efflux. And this quantity here is the material rate of change. And I explained you in some detail in the earlier lecture what the difference between these two derivatives are. Okay, so now what we are going to do is we are going to choose eta as the velocity, this time a vector. For the mass conservation, we chose eta as 1. Now we choose it as the velocity. And then I can simply write dn by dt as del n by del t plus over the control surface rho eta v dot dA. So this I have simply written the Reynolds transport theorem because I wanted to get the substantial derivative on the left and the other terms on the right. Now I am going to choose this as V. So I am going to define P as this quantity that I get n, because now it is going to be a vector. So when I put a V here, let me show you what it looks like. So then this is a volume integral of V rho dV. So recall, rho dV is like the mass of an infinitesimal fluid element. I integrate it over the whole volume, and this then becomes the momentum. So, this is the, so P is the momentum in the CV. Okay. So, that's what is going to happen to this term dN by dt. So, I am now going to write this as dP by dt. This, and then I would put in the term for the unsteady term, and for n I would replace it with this quantity over here, which is essentially V rho dV. So, this is the rate of change of momentum inside the control volume, but this is a local time derivative. Okay. So, this is the unsteadiness part, and then of course, I have the efflux, which is I integrate over the control surface rho V dot, I am sorry, I would like to write it in a slightly different way. So, this I would like to, this will be V rho V dot dA. Okay. So, I have rearranged things a little bit. So, I have taken rho over here, and for eta I put the velocity, and that is the term I get. Okay. Now, this term here is, we are talking about control volume, and we are following the mass inside the control volume at a given time instant t, and how it kind of projects as time goes on. So, this is the rate of change of momentum of the control mass that we are looking at a certain time t, and that by Newton's second law this corresponds to the force F. So, this is the net external force on the control volume. So, what we have been able to show is that the force that acts on a control volume, that actually corresponds to two terms. One is the rate of change of the momentum P of the CV plus efflux. Notice this is a very interesting term. This here is the mass flow rate coming in or going out, because this is V dot dA times the density. So, V dot dA gives me the volume flow rate, and rho would give me the mass, and I am integrating it over the control surface. So, I multiply with this V, and that gives me the momentum. So, that really is your Reynolds transport theorem applied to the momentum. So, I will just rewrite it. So, this is del by del T of, for the volume V, V rho dV plus over the control surface V rho d dot. Okay. Notice this is a vector equation. So, unlike what you did for the mass balance, where you got a scalar equation, this time we have got a vector equation. So, this is going to have different components. So, this, for example, in 3 dimensions would give me 3 scalar equations. In 2 dimensions it would give me 2 scalar equations. So, let me explicitly write that for you. So, suppose I look at in 2 dimensions, I would have an equation for fx and I would have an equation for fy. Fx, for example, would be simply I have del by del t of this volume integral, and this would be now Vx rho dV. So that's the first term. So notice I have assumed that my velocity here is Vxi plus Vyj plus Vzk, but since I am doing on this part of the board a two-dimensional equation, so I have only taken the first two parts. So therefore, this V is simply the Vx. The second term would be the control surface I need to integrate, and I am going to leave this as is because this is the dot product between the velocity and the control surface area. So remember, this was the area with a direction and the unit normal is supposed to be pointing outwards. So at the inlet port, so if I look at this inlet port, for example, this is my inlet velocity and my unit normal is opposite. So V dot dA would actually give me a negative sign. On the other hand, I have a unit normal which is in the positive direction outside, and velocity also at the exit is aligned with this end, so I would get a positive term. So I am going to retain this and only replace this V with Vx. So this would become Vx times rho V dot dA. So that's my x momentum equation. Likewise, I could write down the y momentum equation, which is over the volume V. So now this would be Vy rho dV, and I would have over the control surface Vy rho V dot dA. Okay. So there you go. This is in the vector form, but if you want to write down scalar equations, then in 2 dimensions there are these 2 equations, and there would be an additional equation if we go to 3 dimensions. So this equation makes no assumptions about whether you are incompressible flow or compressible flow, whether the flow is 2-dimensional or 3-dimensional, whether it is steady or unsteady. You can have density that is changing inside the control volume or at the exit ports. So it's an extremely general equation, and yet it has some assumptions which maybe I should point out. Okay, so let's look at some properties here, some assumptions. So I just want to make a few remarks. First, about the force F. So F is the net external force, but recall we have done this in the earlier part of the course. There could be 2 components to it. There could be a body force plus there could be a surface force. Examples of body force could be due to gravity. For example, the weight of the fluid inside a control volume could constitute a body force. Examples of surface force would be because of the pressure, or for example the shear stresses, or maybe the normal stresses. So the stress in general. So they would constitute surface forces. We need to account for all of them when we talk about the F on the left hand side. So that's remark number 1. Remark number 2, so the Reynolds transport theorem is itself valid for all frames of reference. But because we used Newton's law, the force balance equation which is the one written over there, this is valid only for inertial systems. Okay? And what this means is that either my control volume is fixed or moves with a constant linear velocity. Okay? I cannot apply it to in this form, I cannot apply it to a control volume that is, for example, accelerating, or for example moving with a constant velocity but along a curved line. Okay? I cannot do that in this form. It is possible to write the equation in accelerating frame I can do that, but not in the scope of this course. So please remember this, that although we are saying that the equation that we have cannot be written in a non-inertial coordinate system, cannot be used in a non-inertial coordinate system, but that does not mean you cannot do it. You will have to account for certain terms, and there are several references that you can look into. For example, if I want to look at rocket, okay, so a rocket would have, so for example a rocket, I could have a situation where I have some fluid inside and there is some combustion, and then I have hot gases coming out, and this rocket could now accelerate with a certain velocity, which is going to accelerate. This velocity will change with time, and I cannot do this analysis with the equation that I have, but I can write a separate equation. All right, let me see if there is something else that I need to tell you. I think that is about it. So let us understand this with some examples. A jet of water of dia 1 centimeter impinges on a vane. In fact, this is a stationary vane, which deflects it by 60 degrees. And I will show this in a figure. So the jet velocity remains constant at 10 meter per second throughout the flow. Over the vane. You are supposed to find the force exerted by the jet on the vane. So, here is the vane. And there is a jet that comes on it horizontally. So, maybe I will draw that in color. So, that is your jet. The dia is 1 centimeter and the speed is 10 meter per second. Likewise, this is 10 meter per second, and this angle here, the vane deflects it by 60 degrees. It comes in horizontally and then leaves at 60 degrees. And I am supposed to find out what is the force exerted by the jet on this vane if the vane is stationary. There are certain assumptions that we can make. So, we are allowed that pressure does not vary across the jet. So, essentially this pressure is going to be atmospheric pressure when the jet is coming in and leaving the vane, and I can also neglect the weight of the fluid, force due to gravity. All right. So, we need to apply the momentum equation that we just looked at and find out the forces that this flow would lead to. So, obviously, the first step is the choice of control volume. Okay. In fact, it turns out you can choose a variety of control volumes. Okay. It is not just one control volume that everybody should choose. So, I will give you two such examples. Okay. What should you keep in mind? So, first thing is that inflow and outflow should preferably be aligned with the flow. Just to give you an example, if I chose a control volume which was something like this at the exit, so I chose a control volume like this. I can certainly do that. This is a good control volume for the jet coming in because my velocity is in the horizontal direction and the unit normal to the control surface is also in the horizontal direction. So, computing the convective term is easy. But now, if I go onto this part of the control volume, I can still do it. Okay, mathematically there is no problem. The only issue is that the calculation becomes a little bit involved. So, I have the velocity vector at 60 degree, but the normal of my control volume is pointing outwards in the positive x direction. So, what I could do is I could actually choose a control volume that is normal to the surface, right. How about this control volume? So, the suggestion is if I choose this control volume, Then I have both at the inflow and the outflow, the normals are aligned with the flow direction. So my computation would be a little bit easier. As I said, nothing wrong in choosing a straight surface as well, but just you will have to work harder. So that's the first one. The second thing you need to keep in mind is, what about fluid forces and reactions from support? If I choose a control volume the way that I have shown here, then this becomes a control volume. Flow is going in, some flow goes out, and in fact I have sliced the support. So the force acting on the control surface at this point would therefore appear as a force that acts on the control volume. So I'll have to account for it. On the contrary, if I chose a control volume that kind of goes something like this, it traces my finger over the vein, then the force acting on the control volume would involve the shear forces on the vein and the pressure that I would see at the interface of the vein and the fluid. So we'll look at that also as another choice of control volume. So first I want to show you the analysis with this control volume that we have marked. Okay. So let me then just draw the control volume and we'll do the analysis. So let's say this is the control volume and I will draw the vein. This is my vein, and the force acting on this control volume is essentially I have a reaction Fy and Fx. This is because of the cut that I have made over here, possibly to the support. Right? Now if I wanted to look at the support which was over here, as we know it would face a reaction exactly equal but in the opposite direction. So it would see a force Fy and another force Fx in the opposite direction. So this is the reaction on the vein, and this one over here is the force on the control volume. Okay, so I would determine this first by using the Reynolds transport theorem, and then if I take the negative of that, I would be able to get the answer that I am looking for in this problem, because I have to find out the force on the vein because of the jet. What are the other forces that act on this control volume? Well, there is a pressure. So let me show you the pressure, and I would like to show the pressure, let's say in this blue color. So this is the atmospheric pressure which acts on the top surface of the control volume. Likewise, I would have the same atmospheric pressure that acts on the left surface of the control volume. I could also draw the pressure on the right surface and here, and at the bottom. everywhere there is atmospheric pressure. And I come to this surface now, likewise there would be an atmospheric pressure here. So you will notice that there are two kinds of forces that act on this control volume. One is because of the support Fx and Fy, and then there is an atmospheric pressure everywhere. And that's where the assumption that we have been given in the problem is useful. It says that the pressure does not vary across the jet. So I have been able to assume that because this jet is exposed to the atmosphere, so there is atmospheric pressure across the entire diameter of the jet. If I don't make that assumption, then the problem becomes a little bit more complicated, and one will have to work a little bit harder. Now I can go ahead and use the Reynolds transport theorem. If you recall, we had Fx was the x force, then I had del by del t, an equation over the volume, then I had Vx rho dV. Okay, so that was the unsteady term, plus I had an integral over the control surface, and I had Vx times rho V dot dA. Okay. Similarly, I can write the Fy, and Fy would be del by del t integral over V dy rho dV plus an integral over the control surface Vy, and then the mass flow rate rho V dot dA. We already know that the flow is steady. What that means is, if I stand here as an observer and this is a fixed control volume, then nothing changes in this control volume. So if I concentrate on the momentum inside the control volume, okay, I always see the same fluid coming in, the fluid coming in at the same velocity, leaving at the same velocity, and really nothing much is changing. So these two terms go to 0. So really, the force acting on the control volume is essentially because of the momentum change between the inlet and the exit. If I can estimate that, then pretty much the job is done. Okay? I could in principle have a more complicated problem where this velocity of 10 meter per second, which is specified, fluctuates. So I could have some kind of a sinusoidal variation, maybe something like what happens in our heart. Okay? So it beats, and then I could have a flow that not only changes in magnitude, but maybe it also changes in direction. And then this problem would become a little bit more interesting, because then I would have an unsteady term here, and I would not be able to neglect that aspect. Okay, for now we will stay with this. So let us estimate Fx first and then Fy. You will notice that there is this term which is the mass flow rate at the inlet and the exit ports, and it appears in both Fx and Fy. So if I can estimate that for once, then I don't have to do it again and again. Also notice, whatever is the mass flow rate going in is the same which is going out. Okay, so that's constant. So I have a jet at 10 meter per second, the diameter is 1 centimeter, exactly the same thing at the exit. So let's do that. So let me evaluate this term, let's say for the inlet. Okay. So I will draw the control volume again. You will notice this is the unit normal for the inflow, and for the outflow this is the unit normal, and also for V exit, and this is V inlet. So, opposite, and these are collinear. All right. So, if I estimate the terms, let us first look at x equation. So, f x is equal to, I have integral over control surface V x rho V dot dA. Okay. You would have noticed by now that as far as this control volume is concerned, there is the same pressure everywhere. So, pressure does not contribute to any resultant force, and therefore, the only reaction that you get, or the only force that you see on the control volume, are actually these f x and f y. Okay. So, that is what is written over here, and this now I can write as, so at the first I write the inlet term. So, V in is, so maybe I should write here that the V in is actually 10 meter per second in the I direction, and the V at the exit port is again 10 meter per second, but then because I have this angle at 60 degree, so this would become cosine 60 degree I plus sine 60 degree j. Okay. So, I would now like to evaluate this term, and that would be given as first the inlet. So, that would be 10 meter per second, and as far as rho V dot dA is concerned, this would have a negative sign. So, rho is 10 to the third because I am at the inlet. So, as I said, N and V are in the opposite direction. So, rho is 10 to the third, V is 10 meter per second, and my area is pi 0.01 because it is a, the diameter is 1 centimeter. So, 0.01 square by 4. So, this is the term because of inlet. Right. And then I would have to come up with a term at the exit. So, that would be this term, and this would be now a Vx, which is 10 times cosine 60 degrees, and I would have to multiply with this integral over here, the mass flow rate, which actually is same as this, the one that I have written here, but the sign would be now positive. So, I would have again the same thing, 10 to the third times 10 times pi 0.01 squared over 4, which really is the m dot at the exit. This is m dot at the inlet. Similarly, this is the x velocity at the inlet and x velocity at the exit, and if we calculate this, this will turn out to be minus 3.93 Newton. I could now calculate the Fy, okay, and that would be simply integral over the control surface Vy times rho V dot dA. And as you will notice that for the inlet, I do not have a Vy, so it contributes 0 for the inlet. And then for the exit, I have Vy as 10 meters times sine 60 degrees. So, 10 sine 60 degrees times the m dot. rho v dot dA, and that I have already calculated this quantity over here, but it's going to be positive. So that's 10 to the third, which is the density, the velocity, and the area. And if you compute this, this turns out to be 6.81 Newton. So now I have my answer that the force that acts on the control volume is minus 3.93 I plus 6.81 J Newton. That's the force. This is the force on CV. If I want to calculate the force on the support, so this was my support, the force would be equal and opposite. So this force is force on vane is actually negative of this, so it is 3.93 I minus 6.81 J Newton. Okay, so that's your answer. As I promised, I now want to show you a slightly different control volume. Okay, so now we are going to choose a control volume which actually is the interface, one of the surfaces of the control volume is the interface between the vane and the fluid. So let me do that for you. I will leave this as is, and so let me show you an alternate control volume. So first let me draw the vane. So this is at 60 degree. That's the vane. And there is of course fluid, the jet on it that comes in at 10 meter per second, also leaves at 10 meter per second. And now what I wish to do is use a control volume something like this. Okay. So now I have the interface between the vane and the fluid as one of the control surfaces. Now if I try to look at the force on this control volume, so this is my new control volume. What I am going to have is the pressure distribution. So, so maybe what I will do is I will first draw just the control volume for you. So this is your control volume. Okay, so this is the surface of the vane. So what I am going to have is, this is atmospheric pressure on the upper surface. Likewise, I would have atmospheric pressure on this surface, and I would have atmospheric pressure on this surface, again because of the assumption that there is a jet embedded in this, but there is no pressure variation across the jet. I would have atmospheric pressure on this. But now I cannot talk about the pressure being atmospheric on this surface. I don't know. It may be, it may not be. So I will leave it open and I will draw a pressure like this. And let me say this pressure is P which is equal to an atmospheric pressure plus a gauge pressure. In an earlier class, I had explained to you that the gauge pressure is essentially the absolute pressure minus the atmospheric pressure. In addition, because there is fluid here, although I have not drawn it, there are also going to be some shear stresses. So, there is a tau that acts on this control volume. Okay. So, this becomes a little bit more complicated now. So, when I apply now the Reynolds transport theorem, the force acting on this control volume is not just the atmospheric pressure, it is actually now the reaction, the total resultant coming out from this system of stress and pressure distribution. Notice, I really do not have now the force from the vane as such, because what I see is the pressure and the stress that is transmitted to the fluid from the vane. So, now I do something smart. I try to argue that P atmosphere everywhere contributes 0 to the force. So, effectively what remains on this surface is simply the gauge pressure. So, I could just take away the atmospheric pressure from everywhere and just leave what is, so subtract from P the atmospheric pressure and I just have the gauge pressure and I have tau. Now, I could say that the resultant of the tau and P gauge corresponds to the force R. So, I will say that this now the simplified force distribution here. So, let me draw the control volume again for you. So, this is the control volume, and if you recall, the jet was somewhere here. So, this is at 60-degree angle and the flow is coming in horizontally. So, now the claim is that the atmospheric pressure everywhere does not contribute to the resultant, and all the resultant because of tau and P ATM, the P gauge, I could now club it as Rx and Ry. So, this is the force now acting on the control volume, and the net force that acts on the vane because of the control volume would be negative Rx and negative Ry. So, force on the vane due to CV is minus Rx Ry minus Ryj. And I can now go ahead with the analysis with this resultant force, and you will see that the analysis is pretty much the same what I have done here, just the interpretation of Fx and Fy is different. Okay? So, here the Fx and Fy were actually these two forces coming in because of the support, and in the alternate control volume that we have chosen, they are coming out as the reaction from the interface between the vane and the fluid. But otherwise the analysis is exactly the same and you would get exactly the same answer. Alright, so in this lecture what I have tried to show you is essentially how the Reynolds transport theorem could be used to give you the momentum theorem, and how you could relate the force acting on a control volume to the rate of change of momentum. We took one simple example, and this was for a steady flow, and the vane was stationary, the control volume was stationary, and we took two different control volumes and were able to see how to apply this theorem to that. Hopefully, you will be able to practice certain problems and then understand a little bit more. We will continue in the next class. Thank you very much.